Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, we're going to be looking at something old, but it's also something new, and it's something broken. It's a Book8088 laptop, and this was sent into the mail call by viewer Ezra. This was a little while ago. There's the machine. If you're not familiar with the Book8088, it is a replica 8088 laptop. So it's old in that it's using an 8088 processor, so this is an XT class machine. But of course it's new because this is modernly built and it's definitely broken. So in this video, I want to see if I can get this thing working again. And because I'm recording this before I've even looked at this thing, this video might be a complete failure. So without further ado, let's get right to it. I'll put a link down in the description to the original mail call video where I opened this thing up because I did some rudimentary testing in that video. And what's in this little bag here are at least some of the extra parts from this machine. I think this thing has an OPL3 option, which goes right down here. It's a little sound card with an actual Yamaha OPL3 chip on it. So this is that little sound card there, and it has a little board-to-board interconnect right there. And I think 4 little screws, which looks like I put them back in the standoffs. Yay for doing something right for once. We also have a USB port and a couple LEDs, which I think are status LEDs of some kind. On this side, a power switch, looks like an audio output jack for the sound. And on the back of the machine, we have a DC power input, and then we also have a bus connector. And this is actually ISA bus. And there are actually some modules you can plug into the thing to add some expansion cards. Now the case, as you can see, is a little bit translucent. We can actually see the insides. We have a lithium-ion battery, and under this little compartment here, if we pop this off, I think we have a couple ROM chips here, one for the CGA card, one for the internal system itself. And then right here we actually have the CRT-C, the CRT controller that is used for the CGA card. Now this machine, when you power this thing up, does appear to be completely dead. Or I think it kind of powers up but doesn't really do anything after that. Let's just turn it on here, see if anything... Okay, we got some beeping out of it. Okay, well, this is a really boring video because it just works now. Wait a second. Okay, well, I am not kidding that I was done with this thing with the mail call episode. It did not work. I put it away in the original box, and that was that. I don't even know where to think with this. So it looks like these chips are here. I think Ezra sent these. There was a new CRT controller, or actually this is an NEC part here. So we have a new V20 processor here. Then we have a new SRAM chip. This is probably for the CGA. And then this is the original ROM BIOS, which I went ahead and installed a new one. All right, we're looking at something that's like super meta here. It's me watching my own video with myself. It's like I'm commentating on it or something. What we can see in this original video is that what happened when I turned this thing on is I think it did nothing. There was no beeping or anything, and the screen would light up and I would say something like no signal on it. And yeah, it just sort of appeared to be dead. We got some flashing lights over there on the side. I wonder if those lights are doing anything right now. Yeah, with the system actually powered up and working, we're just getting this back and forth flashing there. And I assume that is for the battery. If we look there, there's like a picture of a battery. It's not plugged into the wall right now, hence the lack of charging LED. But we can see very clearly we have a working system. This is completely unexpected. I just can't believe that this thing is actually working. Now the glare though, the glare and the screen, this is a terrible screen. The glare is pretty bad. It's hard to record this. And there's no video output on this machine. That's one of its failings, I guess, so to speak. All right, so back to the video. Is there anything else I need to remember about what I did here? I had it plugged in. Definitely when I powered it up, it'd just say, here, I think I'm gonna do it in a second here. I have the audio turned down, obviously. Oh, look, it's me talking. Oh, and there's Rami. All right, yes, very meta. Myself and myself. That's a younger version of myself. This video's from 2 whole months ago. Okay, so here we go. We turn it on, you would get this no signal. That was that. So it's like the screen module seems to have some kind of a, I don't know, it must go from CGA, because I'm sure this thing outputs a real CGA signal. It goes from CGA to whatever the LCD needs to be driven with. So it's kind of like it has an RGB to HDMI in it. And I think what I want to do actually today, since this video is, I don't know, not going to be a repair video, Let's reinstall everything on this machine, like the OPL cart, and I'm gonna still open it up because I wanna see if I can find those TTL RGB signals and actually output them, maybe from some wires that are sticking out the side of the machine, so we can actually drive an external monitor. With TTL RGB, it's just 5-volt TTL logic for sync and all the video signals, so there's no reason why you couldn't actually have it running the internal screen and an external monitor at the same time. Typically, the output drivers are sufficient enough to be able to actually drive both of those things, and I've done that before with real CGA cards, and it totally does work. Now, just to reiterate on this, if we take a look at the little trapdoor area here, so 8057 is not installed. There's a new V20 that I installed, so I took an extra one and stuck it in there. And I also put this additional BIOS chip that I flashed off of code that I found on GitHub. And after doing that, there was no change in this system. I did that in the mail call episode, and the system absolutely did not work. So between the 2 months that I had this sitting in the box and now, this thing just magically fixed itself. Part of me has me wondering if there's just a loose connection, so let's just turn this off and let's bang this around a little bit, and let's see if that has any negative effect on it. Yep, it's broken again. All right, so at least the problem is back, and this is exactly what it does. The screen just kind of does this refreshing thing, and we did not get that beep anymore. So interesting. Let's bang it this way and see if that makes any difference. Power this on. There it. Now we're getting that. Interesting. So this does seem like it's just a loose connection of some type inside of this thing. And now we're getting nothing again. Now, I'd already reseated all these chips in the mail call episode, and that didn't seem to have any effect. There we go. It's freaking working again. Oh boy. Good quality there. Great quality. Yeah. All right, let's take a look at this BIOS while it's actually working. I have to actually look through the camera view because I can't read this off angle at all right now. Anyhow, we see we have a V20 processor, which of course makes sense with what we have installed in here. We're running in CGA 80x25. We do not have a math code processor installed. There are no COM ports on this machine, which is totally expected, no parallel ports. For some reason, it says we have floppy drives. Maybe that has to do with the USB port that's on the side. Maybe it emulates a floppy drive. We have 640K of conventional memory, and then BIOS ROM extensions are at F00000, and I think that is basically the XT IDE. And of course, the disk is not installed. I have the compact flash card removed. And this is the normal XT IDE stuff here at the top. Let's hit Control-Alt-Delete. I don't think the keyboard is actually working. So even though this thing is working, I'm hitting Control-Alt-Delete and nothing is happening. So this was included with the machine from Ezra. So let's try booting this thing up. Let's see if this thing, with a power cycle at least, power it off, power it on. Is it actually able to see that card? All right, testing RAM. Let's see if I hit escape. Oh, okay, the keyboard did work. Oh, it's got flicker. Like it's got snow there. So it does see the flash card, and it's, oh, whoa. Why is it so slow? Look at how it's updating the, when you scroll. That is far worse than that. What's happening? That is not normal for a CGA. It should not, I mean, you're gonna get flicker, but it shouldn't be that bad. What I wanna do is get this card out. Wow, you really have to use your fingernails to get that out. And I'm gonna put my card in there. My card is, well, let's just say it's filled with all the usual utilities that I do testing with on the channel. Now, from my understanding, the CGA circuitry that's on here is a replica of the original CGA card. And I think it's somewhat compatible, hence the, oh yeah, no high memsys. This is not configured for an 8088. Let's reboot, and I'm gonna hold down the shift key. For whatever reason, there's a .com key right here. It just shows where the keyboard is from. That is hilarious. I do have to wonder, do these keys work? I can't imagine they do. And is the computer frozen? Because it should have exited out of this stage already. Okay, I power cycled the machine, holding down shift. That actually worked. The performance, again, of the BIOS routines are unbelievably bad. Now, I'm wondering if the bad performance on this thing right now has something to do with the open source BIOS that I actually have installed on here. It could well be that that is what's causing that, because CGA itself does not have its own BIOS. That extra CGA chip we saw on the bottom is actually something like a character ROM. All right, so I just edited the auto exec and the config sys. Let's reboot the machine here. Now it should boot normally. That beep sound is a little bit loud and annoying. It looks like on the reboot, it doesn't synchronize the screen properly, and like cuts off. Right. Oh, I didn't take everything out that should have been out. Let's take a look at Top Bench from Jim Leonard. Let's see if this thing is actually performing at the speed I would expect this thing to be running at. I don't know if this runs at 4.77 megahertz or if this actually runs at, say, 8 megahertz, like a Turbo XT. Now, this horribly slow performance might well be what you get with CGA on Top Bench, for instance, running on a 4.77 megahertz machine, but I don't think so. And I know for sure typing DIR on a CGA 4.77 megahertz 5150 is far faster than the way this thing looks. Performance-wise, we're as good as an IBM PC Junior running at 4.77 megahertz with a V20, and those results actually, the ones we're looking at right there that we're comparing this thing to, were submitted by Jim himself. Now, interesting is we take a look at the MEM test, a little bit faster on this machine. MEM EA is about the same and opcode is about the same. So absolutely, this machine seems to be performing at regular 4.77 megahertz speeds. And I just don't understand why the BIOS routines are so slow when you're doing a DIR command. That's, I guess, the only thing that's out of the ordinary. I guess I'm just not used to seeing Top Bench load on a real 4.77 megahertz machine and see it going that slowly. Now, I did a little quick Google because I don't even have a manual for this thing, and I really don't know anything about the Book8088, but I found this thread here on VCF talking about some function keys that actually do work. So, first one is function 1 for mute. That doesn't do anything at all on this machine. Function 2, sound on. Function 2, sound off. Nope. I mean, there's still a beeping or a clicking coming out of the machine. The only thing I'm thinking is maybe those sound on, sound off thing only has to do with this OPL2 card. All right, the next one that's kind of interesting is function 6, turbo mode with no indication of mode. Let's press that. Function F6. Oh, that worked. This machine now gets a score of 9, which is the same as an overclocked IBM PC Junior running at 8 megahertz. The PC Junior 8 megahertz speed are those scores, and these top ones here are this machine, and you can see they're all a little bit faster on this machine than they are on the PC Junior, so probably means that the clock speed is just slightly faster on this. Now, in case you're wondering what that flickering is, that is not a fault. That is actually the original CGA adapter from IBM did not use dual-ported memory or any strategies to avoid corruption if the CPU was updating the video memory while it was being drawn to screen. And that's what's going on right here, is that the replica CGA card that's in this thing right there is actually replicating this original card, which has the effect of causing this snow. Now, one way the IBM mitigated that snow in regular DOS programs is whenever scrolling was happening in DOS, like if you type DIR, whenever the scroll happened, which was when the screen had its video memory being updated, it would actually blank the video image at that time, and then it would come back and it would have the next frame of video. So it has the effect when you type DIR as every time the screen scrolls, which is when it updates, it actually goes away for a split second and comes back. It's a little bit of an annoying thing, and later CGA cards, like that awesome VTech card that I showed off on the second channel recently, did away with that problem. And they used two different strategies for making that happen. They either used dual ported video memory, where the video memory could be accessed through one set of ports for drawing to the screen, and the CPU could access it through the other set, or it just used a strategy to make sure that anytime the video card was drawing the screen, it would not allow the CPU to read or write from the video memory. And the CPU could only access the video memory during the vertical or horizontal blanking intervals, which are around the edges of the active picture. Now, looking back at this post here, it seems like the rest of these functions aren't really particularly useful unless you want to use these extra keys. And mode 80 is just like, I guess, puts the computer in 80 column mode if it's stuck in 40 column mode. The post is also talking about the Sergey BIOS. That is actually what I ended up putting on this. So yeah, this is the GitHub BIOS right here. That is what's on this machine now. I think the original BIOS chip that was put on here used a lot of this code or all of this code without any attributions. So it would be a license violation specifically. All right, back on the thread, looks like we have a few other mods for the machine. So there's a hack to add DRAM refresh cycles back to the hardware, which makes it far more accurate, I guess, running at 4.77 megahertz. It's like Freddie, who's also the person working on the awesome PicoMem project. I did talk about that very briefly on one of my mail call videos as well. Has an improved driver for the USB port. That's pretty cool. Looks like Joshua did some work on getting a USB mouse to work. Looks like there's a resistor mod to make the screen brighter. And it looks like on board there is a 10-pin header that is for CGA output. It mentions schematics for this thing, so I guess we need to go find those. because I still do need to figure out why this thing seems to fail working as soon as I bang it around a little bit. I found a post on Ars Technica from Andrew Cunningham about this machine, and there are some teardown pictures, and it looks like this thing is absolutely just using single board construction. Now it does have these large ICs, and they are in sockets, at least on this picture here. And I'm wondering if the problem is that some of these are just loose, and that might be why banging the computer around seems to change its functionality. So it might be as easy as simply pushing these back in. Now with this machine having been on for a little bit of time, there's definitely some warmth right here over these large chips. So let's just pop out the 9 screws that this thing looks like it has on the bottom cover to hold it down. All right, so it appears that the screws don't let the bottom cover come off. Actually seems to remove the top cover here. How does this all connect up? All right, so there's a thin membrane here for the keyboard. Typically with these little things, you have to either flip it up, there we go, and that comes out. I was gonna say the other possibility is sometimes it slides that way and then you can slide the ribbon out. We have a cable here, which I'm assuming is like a power cable for the inverter board or whatever, the driver board that's in there. And then here is the driver for the LCD. So we'll just connect that. And then there is another little cable right here, which maybe is like a backlight power cable or something. Once the top is removed, looks like we have another set of screws to remove here that takes the PCB off of the bottom frame. And it looks like the battery has some adhesive that holds it onto the bottom cover, or is it the top cover? No, it's the bottom cover. So we're just gonna use this plastic spudger here to disconnect the battery cable. There's the main board. It's exactly how it looks in the photographs. So there's that battery that's left behind. And looking at this, I think what we see here is a lot of the logic consolidation into these large ICs that really makes this thing possible. So if you look at the original 5150 motherboard, 5160 motherboard, there's a whole plethora of chips, Intel chips and stuff like that. And of course, on later XT motherboards, that was all condensed down to chipset ICs, which were soldered onto the motherboards and greatly simplified things. Problem is, those aren't really available anymore. I mean, maybe you can find some new old stock or ones that were removed from boards, but when it comes to manufacturing something new, well, I'm not quite sure what they did here. Did they actually recreate that stuff, like here in this XTIO chip? And looking here in this area, we have some system memory. We also have this chip right here, which it says there is the DMA controller, the 8237. So that is still available as a discrete IC. Compact flash card is at IO address 300, and there is a USB controller, which is this IC right here, which is found at IO address 260. Of course, that's not something that's like normally found on an XT, but you could easily connect one of these to any XT, and it's available on a regular IO port. These are bus transceivers right here, 245s. These are 573s, which I think off the top of my head are latches. And I think I recall seeing somewhere that obviously the creator of this project took these two ICs along with the CRTC, the font ROM here, and the SRAM for the video memory, and put that on an ISA card for a new modern CGA card, which uses this circuitry right here. Now, when it comes to adding CGA to this system here, there's that expansion header J6 that was talked about in that post. And I am positive that that is exactly what this is. This is CGA. And if we flip this over here and we take a look at what's going on the board here, you can see here there are non-installed resistors, which are either going to be protection resistors or they're going to be some kind of a jumper. And then that makes its way over here, and there's some additional diodes and whatnot. And look at this, it actually goes to the header here that goes off to the LCD. All right, first things first though, we need to see why this thing's not booting sometimes. Let's see if these chips are even loose in here. Well, that one was in there pretty good. Oh, that one was totally in there loose. Oh yeah. Okay, this one? Oh, this one as well. Maybe I can show you what this looks like, but this is what a pushed in chip looks like. You see that right there? And look how this one here is right up at the top. If I give this thing a good push, like that, it is now properly seated in that socket, just like this IC. I think at some point this thing must have got bumped and the chips sort of popped out. Now that one there is actually in all the way, and it actually sits, well, a little bit proud of the socket itself. It's a low profile socket. But these ones here, they needed a good push. Okay, I just reconnected the battery up. All right, so we have power LEDs, but we don't have any beep. This thing is not working again. So I'm just gonna tweak the board a little bit. Okay, so it's working. Now if I tweak it the other way, well, now it's working. So what's going on? We have some kind of bad connection on here, clearly. This looks like rework right here on this RAM chip. So this thing has had some repair work already done to it. Looking at the way these are soldered to the board, this all looks like it's machine done. But you see how messy this looks right here? My only assumption is there's probably some issue going on right here still. So let's just push on this chip right here. I just want to see if, like, you know, bending this board results in this thing not working. So far, it's okay. But this machine absolutely was not working when I first plugged in the battery just a moment ago. So we're still not out of the water entirely here. There we go. It's dead again. So what exactly is causing this? Let's push on things. All right, so the I/O chip maybe? Right, so it's dead. I'll push on the chip. Still dead. Let's give it a harder push. Well, I'm going to pop out this I/O chip here. Let's get this out of the board. Without this, obviously, this system is not going to work at all. Like, I can turn this on and we're going to get that dead behavior. Yep. So what are we dealing with here? Are we dealing with a bad connection on one of these pins? These do look a little bent. Interesting. Why? Why are these not just perfect? I assume this thing is a new chip and not some kind of new old stock. Yeah, these pins are in kind of rough shape. There's like a little bit of something down there, a little something something. I don't see any corrosion on these legs. They just are a little flattened and slightly mangled. So one thing you can do with these PLCC chips is you can use like a pick or something and you can actually bend them out, which just makes them contact the socket a little bit better. And then of course, I mean, Adrian's Digital Basement here, right? I'm gonna put Deoxit on this. Okay, so all of those chip legs have been pushed out a little bit, so they should make slightly better contact with this low profile socket. Now, unfortunately, this is surface mount. There's really no way for me to check to see if those legs are all connected, but I'm assuming, I mean, there could be a problem with this socket here, and that might also be the issue here. But I'm just gonna put a little bit of Deoxit on all these pins just to help things out. All right, you give this a firm push down. And let's see, did I make it worse or is it the same? It's not working now at all. So yeah, the system is on, the lights are going there, but we have no one home. Really feels like it's in this area here, doesn't it? Pushing on the PCB itself. That didn't do anything. We push on this IC. Interesting, it starts working, let go. Not working. Push on this IC. Okay. No change. All right. This IC right here, it really screams that might well be the problem. Let's just get this out. As you can see, that we have an Harris IC from 1995. This IC might just be flaky. Luckily, there's nothing custom about this chip, so it would be totally doable to find a replacement for one of these ICs. I could just steal it off another board as a temporary test as well. Let's just put some Deoxit in that socket there. Make sure that's all the way in. Turn it on. Nope. Let's push down. No, system is not working now. Could well be a bad socket though. Let's push down on this IC again. Yeah, so it seems like I've made it worse. Let's try to get it all in the view here just so you can see what I'm doing. So turn it on. All right. All right, yeah, it's got to be this Harris chip. Maybe I should just reflow these solder connections. They look okay. I don't see anything that looks bad, but can't hurt to just reflow them, right? So I'm just heating up each pin till it moves, and there's plenty of fresh solder on the tip. So if anything's missing from one of these, it will get wicked in. Okay, there we go. Let's pop this back in. Do we have a working system? Well, we do now, but I gotta bang on stuff here. And it's dead again. All right, here's the data sheet for the Serenesys version of this chip. It's a CMOS bus controller. I think this generates some of the ISA signals that are used on ISA bus. This works with various 8088, 8086, and, well, early processors all the way up to 8 megahertz. Here's the block diagram for this chip. It takes some signals that come from the CPU there. It takes a clock, an AEN, which is also from the CPU, various control inputs, and then it outputs these logic signals. Now it says here multi-bus command signals. Is this compatible with ISA bus? I'm assuming it is because this thing has a compatible ISA bus. And it has these other signals here that go and drive the data transceivers. That's the 2845s and things like that. Now, with the system sitting here on the bench, it's not working very reliably right now. It just doesn't seem to start up at all. If I pull it towards me, the system pretty much works. If I push it away from me, it does not work. I'm really wondering if this is just a bad socket. I know I reflowed it, but this really does seem to be specific to this chip. And I say that because I'm just gonna pull over on the chip in the socket here, and the system is running there. And if I let go, it doesn't work. So I was careful not to apply any pressure to the PCB itself or any of the other ICs in the area. I'm just gonna basically squeeze between the chip and the socket there. Oh, and look at that. I mean, I think that pretty much confirms it's either the chip that's bad or it's the socket that's bad. All right, so I just popped the chip out of the board ever so slightly, and I'm just gonna push it in partially. There we go. It's not running. I'm gonna push on the chip. Very interesting. Now, everything looks okay on the chip. I mean, the legs are a bit bent up, so this obviously came out of something else. So we'll just straighten these out a little. Oh, one of the legs just came right off. The little leg, it's over here on my bench. I did not bend that. I did not bend it over. That must have just barely been hanging on. I'd say this is one of the issues with chips that are pulls from things, because you just don't know if someone's gone ahead and, re-straighten those legs, and you end up with ones that are just ready to absolutely fall off. And you can see that one of these is longer than the other, this one. So I don't know what's going on there. All is not lost. I'm just gonna solder a new leg onto that broken pin. All right, I have a dead EPROM here. I'm just gonna borrow one of the pins, steal one of the pins off this, bend it around until it metal fatigues right off, and then you end up with the pin. So we'll just tin what's on the IC itself, and then I'll tin the leg itself, the one we're gonna be soldering on. It's attached to the iron right now. That is fine. And then we just get these connected together. It doesn't have to be perfect, it just has to be attached. All right, there we have it. I'm just gonna trim it off so it's exactly the same length as the rest. And while it's kind of ugly, that should do the trick. And will it work? No. So that was not the problem. Let's just move this again. So that pin that fell off was absolutely not our issue. I think what I'm gonna do next is I'm just gonna replace this socket. There are the reminiscences of the socket. There's a new socket installed in the board. It's one of those machine type sockets. I like those a bit better. I know there are lots of people who don't, but I do, so that's what's in here. So have I made this worse? It seems like I have. Well, at this point, the system appears to be totally dead in the water. All right, I think I'm gonna have to break out another system. So this thing is totally dead. Let's just try one more time. Yep, absolutely nothing happening now. Well, I have another motherboard here. This is an XT clone motherboard, and it actually has that same IC right here next to the Mathco processor. If we turn this thing on, well, it's not working. This machine worked literally a moment ago. And I can tell because we're not getting any postcodes on here. We had postcodes and I had a beep and everything was hunky-dory. And now the system is dead. Oh, I'm not batting 1,000 here. I am really, really striking out on this system. Why did this system work literally a moment ago and now it does not work? All right, well, anyhow, the chip we're looking for is right here on the motherboard. I'm just gonna take this out and we're gonna pop this into the other motherboard, into the Book8088. What I was hoping to do is actually take this 8288 and stick this in the other motherboard, which was working a moment ago, And that would be a perfect test. Oh, the one I'm putting in here, by the way, it's a UMC part. Okay, the UMC part is in. And it freaking booted up. It freaking booted up. That means that this Harris chip, I'm assuming, is going to be the faulty part. Let's just give this the old push on this area here. Yeah. Unbelievable. I guess there's just something flaky about this chip on the inside, perhaps. I wish the other motherboard worked. Right before I started recording, it worked. I promise you it worked. And I was intending to swap these and then take this Harris part from here and put it in the other motherboard and see if that did the trick. I was just about to put the XT motherboard away and it's running now. So the postcard has a code of A8 on it. Now, XTs don't really have postcodes, but if I pop a video card in here, this machine will actually do something, usually. Oh no, it froze again. Yeah, it says F0. Yeah, okay. I have the chip in the motherboard that actually came from this, and that's what was in there just a second ago when this thing actually did boot. What happens is you should start to see random postcodes on here when the motherboard is working, and it is not doing that. It's coming out of reset now, at least. No, now it's stuck in reset. There just seems to be another flaky chip on this thing, and I don't know what it is. Now, I did put the V20, the one that came with the Book8088, into here. Maybe that's a flaky part as well. I'm just for sure, I'm just gonna remove this and we'll pop in a known good processor in here, and not this one that I wasn't able to test before. Here is a nice Intel 8088. I think this is a 4.77 megahertz part, and that's fine. This is not a turbo motherboard. Let's just pop this in here. Actual Intel part here. Okay, it's posting. So let's plug in the video card here. Let's see, maybe that chip was flake as well. Yes. Okay, you gotta be kidding. So this V20 might also be a dodgy part as well. I thought this was dodgy. In the mail call episode, I thought this looked rebadged. That is not what's in the Book8088. It has a real 8088 in there now. Let's pop out the 8288. So this is the UMC part that was on this motherboard, and it was actually soldered into there. And we'll take out this Harris part that was on the Book motherboard, and I'll stick this into the motherboard here. And absolutely, it is not posting there. You see the two dashes on the postcard? Let's power cycle it again. Same thing, just two dashes. I'll put back in the UMC 8288 there. There we go. All right, well, that pretty much confirms that this chip here is absolutely dodgy. And my assumption is when I was pushing on it, that was somehow making it work. Maybe there's like a bad bond inside one of the legs that goes into the body of the chip. Who knows? But it seems to be completely dead now. Well, and we just pretty much confirmed it on this motherboard. All right, so the next question is this CPU here, this V20 that came in there, also bad? Let's remove this 8088, which does appear to be fully functional. It's quite warm, but that's normal. And we'll put back in this sketchy, absolutely repainted V20 here into the motherboard. It did post, so I know this chip does sort of work. It's not totally dead, but it appears to be flaky as well. So into the motherboard it goes, and yep, not posting. Same thing, we're just getting dashes. Wow. Just for the final confirmation, I'm just gonna put the true genuine Intel 8088 back in the motherboard here. Power this up. There it is, posting. All right, well, I'm gonna say that this chip is also bad. So 2 bad chips in the Book8088. So that means that that socket I took out of here probably wasn't bad, but that's okay. I don't mind putting in one of these machine sockets. I just find them a little bit better anyways. So the UMC 82C88 is in the motherboard, and we turn it on and it just works. And let's bang on it, bend it, do stuff to it. Yeah, okay. So even though these weren't really pushed in all the way, that could have been an issue, I don't know. but pushing them in all the way didn't really help anything. It was a red herring that the 82C88 was actually just a flaky chip. I thought the socket was bad because you saw me pushing on this and it would sort of work, but no, the chip itself was actually bad. And incidentally, the chip that's in here now is from 1986, 16th week. Well, the diagnosis that I did here was a little bit backwards. I like to kind of try to see the problem, but because everything was in sockets, it was really easy for me to sort of push around, take things in and out of the board and whatnot. And that definitely brought me to that chip as being the flaky one. Now, on the other hand, I think it was kind of lucky this chip started working, because if it wouldn't have started working, it would have been much harder to figure out what was wrong on this. Because at that point, you're just blindly going around the board and you're checking for signals in and out to try to see if you can see missing signals that are keeping the system from running. So now I know this is the bad chip. Let's scope all the signals on the good chip while the system is running, and then let's put this into the board and see if we can try to identify maybe a signal that's not working. To help me more easily probe all 20 pins on this, because doing it on camera is a little bit difficult with the camera over my head, I'm going to use one of these chip clips. So this just clips on top of the IC itself, and then it gives me these pins on the top. It just makes it much easier with this on here for me to get to these backside pins, because I'm looking at the board this way, right, with the camera overhead, and that way I can just very easily probe these. And we'll start at pin 1, which is just low, and that's what we saw before. And then that's the clock signal. Pin 2. Pin 3 is lots of activity. It's the S1 signal. Pin 4 is the DT/R signal, so we see plenty of activity there. ALE is pin 5. We got activity. AEN, don't see any immediate activity, but let's power cycle the computer. No, don't really see anything there, but maybe that's just normal for this particular computer. Pin 7 has activity. Power cycling the board, just stuff happening. Pin 8, plenty of activity. Pin 9, we got activity as well, and then 10 is ground. Pin 11, which is IOWC, if I zoom in and out here, we can just see it has this pulse. Whoops, I lost the trigger point there. So we zoom in, there it is. All right, check this out. Check out the width of the pulse there on pin 11. Pin 12, it's a little bit wider. Pin 13 is a little wider yet. Pin 14, we see 2. And what's this? This is pin 15, CEN. This looks like it's tri-stated. See how it's sort of floating in the middle there? So that just must be normal for that particular pin. Here we are on pin 16, DEN, plenty of activity. Here's pin 17, the MCE pin. Then we're on S2, pin 18. Pin 19 is S0. So we got activity there. And then we have VCC, so that's 5 volts. Now I'll swap over to the non-functional chip. The issue is that there's a lot of complexity going on with the Intel type systems like this. And I don't really fully understand the way it's all supposed to work. So like, what are the input signals? What are the output signals? What signal missing from this chip causes this to not boot? So the chip's in there. Let's just make sure that it doesn't boot. Yep, okay, we're still dead. And now I wish I could remember how everything looked. Pin 1 doesn't have anything, which is expected. That's the clock, which we know we have good. So S1, this signal here had stuff on it, and there is a little bit of low there for a second, and then it just stops. Oh, okay. We still didn't have a booting system. We didn't hear that chime. I'm on pin 4 now. If we power cycle the computer, we have stuff happening, but the computer's not booting. All right, so this is pin 5, ALE. I could have swore we had activity on this pin. And that does not look right. Now we have to see if ALE is an input or an output. If we scroll down here, ALE is an output signal. Now this could be our problem right here. That's the bus driver on that particular pin on ALE. Let's just double check by swapping back the other chip. Pin 5, if I turn it off, we should have activity. So you saw it was sort of, there was what looked kind of like activity there, but not quite, right? It wasn't really going down properly. The working chip is back in. System is running. So 1, 2, 3, 4, 5. Okay, and I'm on pin 5. And yeah, we have a good signal here. And this is an output signal. So right there, that's kind of telling us that we have a bad output signal on that chip. Now, one thing we can do here is I can pull out this chip, and let's look at what that pin looks like on the motherboard with that chip not installed. 1, 2, 3, 4, 5. Okay, I'm on pin 5 and we turn it on. Okay, so we're not really getting anything. It does float high. We're at about 5 volts, so that's normal. Let's check out pin 5 now. Well, pin 5 looks good, actually. 1, 2, 3, 4, 5. Oh no, pin 5 doesn't look good. Oh, it kind of comes and goes when I push on it. It kind of comes and goes. And if I push on the chip, towards the body of the chip, it does that. So let's hold I'm going to hold the probe on it, and we're going to power cycle the computer and see if it runs now. Oh man, that is it right there, everyone. We can actually see the failure. So it's failed right now. And if I push on the chip, on the leg itself, there it is, it starts working. And if I power cycle the computer, no, the signal's bad still. I got to push up towards the top. There we go. I'll turn it off and on. Yes, that's it. So confirmed, we can see the fault. There must be something going on, now this is the good chip, where the leg goes into the body, like some corrosion or whatever, and pushing on it, like physically pushing on it with the probe, actually makes it connect, and we'd see the good signal. But as soon as I let go and I touch it very lightly, or I touch it near the bottom, we'd see that kind of signal that's not really there. And with the pressure on it, the system working, as soon as I pull the probe away, the system instantly crashes. So we've kind of confirmed right there that that is the fault with this chip. I mean, that's one of the faults. Who knows what else is wrong with it. But this chip is dodgy as. So that's good. I'm glad to know that we can actually see the fault on here. Now, of course, if you were just probing around on this system and you didn't know what it should look like, it would be difficult to know that that was a bad signal. Like, we know it was bad because I could see it changing, or when we had the good chip in there, what it looked like. But I have to admit, it didn't look bad enough. It was sort of just, there was a little bit of signal up at the top that would kind of give me a clue that it was trying to drive that signal down to ground. But honestly, you know, TTL logic is noisy, and something that's up near 5 volts, if there's a bit of noise up there, that's often totally normal. I mean, you look around the Commodore 64 at those logic chips, these are CMOS chips actually. So CMOS drives the bus much harder than regular old TTL logic. You look at a 64 and it's just noisy all over the place. So it's very difficult to look at signals, and if they're at 5 volts or at 0 volts, it's hard to know if that's a fault or not unless you know for sure that chip should be toggling that output, for instance, based on the inputs. When you see something on a 64 that's at like 1.2 volts, or it sort of goes up to 1.2 and then down to ground but never goes above 1.2, well, yeah, that's a problem. Or vice versa, if you see something like up near 5 volts and it's kind of pulling down to 3 volts to go towards ground, but it never gets all the way to ground, stuff like that can be a little bit more of an indicator of an issue. But this one, that's a really tough problem to solve. Now, I'm glad it was something that I happened to have a spare, so I was able to test this thing, and yep, I have the working one in there, and it's just running now. And if this was a problem on one of these custom ICs on here, well, there would be absolutely no way to fix it, and it would be very, very difficult to troubleshoot. All right, so we know the system does appear to be working. We have 2 flaky chips, the CPU, which, yeah, I guess it's kind of flaky, as we saw on the other board, and this CMOS bus driver here. So next, let's try to investigate the CGA output and see if we can get that working, because with CGA video output, I could bring an actual 1084 computer monitor and bring this up to one of the computer meetups I might go to periodically and have a little portable XT machine. You'd have to use the keyboard on here. You can't plug an external keyboard in, but nonetheless, that is still kind of cool. And with a real monitor, you're not stuck looking at that frankly awful LCD screen. We have to figure out what these pins go to. So we know that there are these resistors that aren't installed here, and this makes its way over here to this section here, which goes to the LCD screen. And there's a little piece of metal on my thing there. When you look at these resistors installed here, these diodes, this appears to be a voltage divider. I wouldn't be surprised if the LCD screen takes analog RGB, so 0 to 0.7 volts for RGB. And you notice there's just RGB. There's only 3 signals that go here, plus these 2 at the top. These are probably sync signals, horizontal vertical sync. And this is converting the digital TTL signal, which I assume is on this board, into something that's analog. I bet you what this is not doing is that the dark yellow color is actually not showing up as CGA brown as what it should do with the IBM CGA standard. Is probably just a light yellow and a dark yellow through here. I'll have to check that later. But if we move over here, I put a dot right here on what I think is pin 1. And I just looked at this connector here for the ISA bus, and it has the same pin 1 right there. And the way these headers go when it comes to pinout, as opposed to being 1 through 5 on one side and 6 through 10 on the other side, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now with these resistors here that aren't installed, that's going to keep this thing from working. But if we look at the ISA bus, there are tons of 4.7K resistors installed here between, whatever the logic is on the motherboard and the expansion header. So I'm just going to do the same thing on this once we figure out what the pinout is. And to get 4.7K resistors, I went ahead and I just found this junk board. That's an old router or whatever. And it turned out that the resistors that were right here were all the 4.7K that I needed. And there they are inside here, ready to be installed on this board. Now, when we look closely at this, we can tell that there are, looks like 4 pins that are grounded. These 2 right there and those 2. But luckily that leaves enough for CGA because we need RGB, that's 3, plus intensity, that's 4, plus horizontal and vertical sync, so that's 6 total. And that matches up with the number of resistors that we have here, which is also 6. And yeah, if we look over here, remember we're only getting RGB and I guess the 2 sync signals. And yeah, I think the next step is I'm just going to install the resistors onto here and then we can scope out the pins here to try to figure out what is what. We have all the 4.7K resistors installed and I did double check that none of them are shorted. And yeah, sorry, I'm not using the microscope and the soldering is really ugly, but I just did this by hand and it's absolutely good enough. So now it's time to figure out which pins are which. Now, with the system just powered on, I'm not gonna be able to tell which are RGB pins, but that's fine. We can figure that out later. The intensity bit should be able to be seen. And then of course we have the 2 sync lines. And these are the CGA signals right here. Pin 7 composite sync is not actually used on a regular CGA monitor. I think pin 7 is actually used for monochrome video, but on the Commodore 1084 in analog RGB mode, pin 7 is used for composite sync. But in this case, we won't need to connect that at all. Now the pins should be active now that the resistors are in place. So this is pin 3. And that is a sync signal, 15.7 kilohertz. So horizontal sync, perfect. And then the next one over is going to be vertical, looks like. And if we zoom in a little bit more, 59.8. So that is the horizontal sync. Oh, and I'm sorry, I think I just misspoke. Pin 3 is actually vertical and horizontal is pin 4. Pin 5 and 6 are both grounded. I can see that on the PCB. Then we're on pin 7, and then this is going to be a video signal. I'm just gonna have to make an assumption that this is gonna be red. Probably just whoever laid this board out did that as red. The next one looks the same, so we'll say that's green. And then the next one, blue, I guess. And then the final pin 10 doesn't really have much on here. So this is gonna be the intensity bit. Just probably because of that BIOS boot screen, there's only a little bit of text that actually has intensity enabled. So that actually breaks down right here. And I made a Google Sheet here. So we have CGA on the left and Book8088 on the right. And there it is, intensity pin 10. And I think this is going to be how we hook this up to the RGB to HDMI. So I'm just going to make the assumption that is RGB like that, 7, 8, and 9. What I'm going to do is use this little ribbon cable here. I only need 7 conductors because it's RGB, intensity, H-sync, V-sync, and 1 ground line. There's not a lot of load on the digital signal. That's why these 4.7K resistors are just fine. So this is going to be perfectly fine. And I'm honestly going to just solder those on to the pin headers here. And I'm just going to drill a hole in the case because you can kind of see that it looks like there's space right there for this pin header. Now, if you want to do this in a nice way, buy the appropriate narrow pitch pin header here, kind of like the ISA connector right here, and use a Dremel or a nibble or whatever, make a perfect little square hole, and then you can have this actually header exposed there once you've installed these resistors. And then you just need to make a little adapter that goes from this to the DE9 or your monitor cable or whatever. But for me personally, I don't really care. I'm just going to drill a hole in the case right there. I'm just going to run this ribbon cable right out, and then I'll just attach a female DE9 connector with a little hood on it and just have that hanging off the back of the computer. I really don't mind that it hangs off like that. I know that's really going to bother some people, but for me personally, that's completely perfect. And then I can just take a normal male-to-male 9-pin cable and plug that into a monitor, or even take a CGA monitor as a built-in cable and just plug it straight into the DE9. And we're good to go. I don't need to have a dongle that I'm going to lose or whatever. It's just going to be connected all the time. All right, there we go. The ribbon cable has been connected. I double checked that none of the wires are shorting into each other. I haven't yet connected anything to the other end, but I'll just do that in a moment. And bottom side of the board is kind of ugly, but you know what? It's gonna work just fine. There we have it. The DE9 is connected. Now I may need to swap around the RGB line, so I'm not putting the hood or anything onto this yet, but we can actually test this out with the RGB to HDMI. So this cable here goes to the RGB to HDMI and is wired up for normal CGA style input. And it looks like we're already configured for CGI. So let's turn it on to see what happens. Well, seemingly nothing. Well, RGB to HDMI is telling us that no sync is detected. So let's poke around on the outputs while it's connected and see if those 4.7K, maybe those are too high, those resistors, and it's pulling the signals down too low. Okay, I'm gonna go right off the 9-pin connector. So that should be red. Oh yeah, that's gonna be way too low. Well, clearly that's not gonna work. That should be green. That's blue. And if we flip this over and we look at the two sync signals, yep, we're getting 1.8 volts there on that sync signal. It's way too low. And this one also 1.9 volts. And the intensity bit, yep, just a little bit. We're getting that low signal because there's a load on those lines, and the 4.7K, I guess, is just too much. Now there's a version of the RGB HDMI that has a buffer in it. So it has like a bus transceiver on the input stage. I think this version though that I'm running, it just feeds these signals directly into the CPLD. Now the CPLD that's on there is a 3.3 volt part, so it should be fine with that, but maybe there is some type of termination resistors inside the board on the RGB HDMI. I can't remember how it's designed. So what this tells us is those 4.7Ks are just too much resistance. All right, it's the next day now, and I've sort of mulled over the problem that we were having here with those resistors causing the TTL levels to be too low. My biggest problem with this particular device is it doesn't appear that the TTL outputs are buffered in any way. One of the large ICs on the main board that generates the CGA graphics seems to be what's outputting those signals. And I'm not really comfortable hooking those directly up to, say, an external monitor using just 0 ohm jumper links. I was reading through that thread I showed earlier in the video a little bit more about people's experience hooking it up to CGA devices. And it seems like people were just putting 0 ohm jumper links there and hooking it directly up to things, usually in RGB to HDMI. That's probably completely fine, but you just don't know with a monitor hooking it up what that's going to do, and you might be putting way too much load on that IC, and it could damage the outputs. Once those outputs are damaged, all bets are off and you're not going to have any display capability out of your Book8088. So I decided to go take a look at, well, the originator of CGA, which is the IBM CGA card, at the schematics for it, to look at exactly how IBM did it. IBM freely published the schematics for the CGA card. I'm pretty sure they did in the technical manual, but luckily someone has recreated it here on GitHub, which is a lot easier to read. So there's a PDF you can download, which actually has this nice recreated schematic. And it's down here on page 6, we have the relevant section that I wanted to look at. So the various TTL signals for RGB, intensity, and the horizontal vertical sync are generated by various chips on the CGA card, and then they all make their way to this single LS244. The 244, unlike the 245, which you see a lot on various old retro hardware, is, instead of being a bus transceiver like the 245, which is bidirectional, this is a single directional buffer essentially. So inputs come into it and you can enable and disable the outputs, and that's it. It just passes right through, and it just essentially creates a really nice stable output that on the IBM CGA card right here comes out and then just goes directly to the DE9 connector. They did attach some capacitors here. It looks like whoever created the schematics here says that their particular card had 47 picofarad. This is a little bit of smoothing. It's not really there for anything else. It's not like a protection or anything like that. So yeah, IBM decided that it was totally fine just to go directly to the monitor. So if it's good enough for IBM, I think it's going to be good enough for the Book8088. And I want to try to replicate this by getting a little surface mount 244 and putting that on the board and removing those 47K resistors I put on here, or 4.7K resistors, and then just connecting the output of the 244 directly to the wire that's going to that DE9, which I've already attached. So I don't normally keep surface mount components in stock, but I keep a bunch of junk boards, and I went onto this old network card here, which is dead, and I pulled off a 244, which is right here, and I have test fit it onto the Book8088 here, and I decided I'm just going to stick this right on the board here. So I just need to take the outputs of this chip. For instance, here's pin 2, which is an input, and the output here is on pin 3. I need to connect that pin over here either to that pad right there, that would have been the other side of that resistor, or I could just connect it right there. And I did actually manage to get some of these pins, I sort of bent them over, connected up to some of those pads, although there were still 2 pads that are not connected to the IC, And I think that's because I'm gonna have to connect them up to input pins that are on this side. The way this chip is wired up, some of the inputs are on this side, some are on this side, and the outputs are on the opposite side. So it's a little bit of crisscross thing going on, but it's nothing that I couldn't do with a few bodge wires. And like I said, hook this up to power. There's probably gonna be 5-volt power right over here on this ISA bus connector. Add a bypass resistor for the power input, and then we should be good to go with a nice solid 5-volt TTL output right on here, while not affecting anything to do with the signal that's going to the LCD screen. Okay, there it is. It's all installed. And it's really ugly, but I think it should do the trick. So 5 volts I'm taking right off here, off this pin, and that goes over here to the 5-volt input here on pin 20. Pin 1 of this IC is up here at the top. This is the ground pin, and I did put a bypass capacitor right here, and I'm picking up ground right there from the header. So it goes there to that pin. And then we have to ground some additional pins on this chip. So I'm not using 2 of the inputs, those are grounded, and this is pin 19, which is one of the enable pins, that is grounded. In addition to pin 1 here should also be grounded, so that's also grounded. They're all sort of commoned right here on this capacitor. I decided not to use any of those pads on the left side where those resistors were. I just went straight to the connector there. And I mean, it's really hard to see, but I just sort of layered this all up on there. And I think it's all good. I went ahead and I double checked that nothing is shorted out. I'm doing a little bit of 3-dimensional work here. You can see the ground lines there are lifted up, and meanwhile, the ones that have signals are on the lower level. Now I'm going to be using some hot glue to just sort of attach this whole thing down, since it is just sort of flopping around. But I think in the meantime, I think we're ready for power up testing just to see if anything smokes. Hopefully no damage occurs when I power this on. Okay, so the oscilloscope is powered up, it's connected, I'm ready to go. I just want to start seeing if we're seeing good 5-volt TTL levels out of the DE9 connector. Let's hope that I turn this thing on. It does power up normally. Here we go. Good sign, everyone, good sign. All right, so we're looking at the blue pin here on the DE9, and it looks good. This is the green pin. That doesn't look so good. And that's the red pin, and that doesn't look good either. Okay, let's power this off. I need to try to figure out what exactly is going wrong here. All right, I think it's fixed. I found a couple issues. I had wired up 2 of the pins wrong on the output side, the, I think, red and intensity, or 2 of the pins, yeah, were swapped. But there was also a short from one of the outputs to the inputs, which is kind of bad because I was putting 5 volts back into the logic chip on the board. So hopefully it was able to withstand that. So let's power it on now, and I'll take a look at the output on here, and we'll see if we see 5 volts and the correct signals on all the pins. All right, we're on the top row here. So this is going to be blue. Then this pin here is green, that looks good. And red, that looks good as well. And if I flip this over, this is the intensity bit. Okay, looks good. There's a little bit of noise down at the bottom, but that's completely fine. This is TTL. Vertical sync and horizontal sync on the last pin 9. Okay, this looks good now. So all that's left to do now is hook this up to the RGB to HDMI. We should have a working signal, and if it does work, I'm gonna grab an actual CRT monitor, and then we'll see if that works, because that's the ultimate test. All right, the RGB to HDMI is connected up. See what happens. Okay, maybe I have the sync lines reversed. That would explain what we're seeing here. We're seeing the correct colors through all this mess here. Ah, yes, okay, taking a look here. I remember pin 9 was horizontal sync and pin 8 was vertical sync. So I just need to swap those around, and I'll do it on the DE9 connector. That's the easiest place to do it. All right, doesn't look like much, but I swapped those 2 lines around. You can't really tell because it looks exactly the same. There we have it, it freaking works. Awesome, all right. So fully buffered CGA output, and look, we can see that static there. And I think we have, yep, so the intensity bit is absolutely working because you see at the top there, the A, F6, A, F8, etc. That's fine. And then the colors there look perfect as well. The book is nearly back together. I don't have all the screws back in. I just have some of them. As you can see, I drilled a little bit of a hole there so the cable can pass through. I'll just dab a bit of hot glue into that so it doesn't get tugged on. If we open this thing up, it all looks good here. I haven't actually turned this on yet, but hopefully everything is working. I did put the sound card back in as well. All right, let's power this up. Okay, good, it's powering up. Okay, good. The screen is still working. I was a bit worried there for a second. We had a little bit of a delay. And there we go. We have CGA output as well. I don't know why you can't hit Control-Delete. Oh, you can. I thought I did that earlier and it did not work. Well, yeah, looks good. There we go. I think the colors are good as well. So here we are in Jim Leonard's CGA compatibility suite, and as you can see, it is rock solid, the video display. Let's check out color here just to make sure everything looks good. Yes, it looks really good. So the color dark yellow is actually brown on CGA. Last time I mentioned that, people asked about it. So you see at the top there, it goes blue, green, cyan, red, purple. These are all dark colors, and then it has what is dark yellow, but notice it's rendering as brown, and it works that way on a CRT as well. There's a bit of extra logic in the color decoding circuit in the monitor that basically adds a little bit of extra red to the dark yellow to make it that brown color, because otherwise you'd have the light yellow down at the bottom, and then that brown, which is right about there, would just sort of be the same shade of yellow, but just darker. And it looks like on the LCD, they're attempting to add a little bit of extra red into the dark yellow there to make it a bit more brown. It doesn't quite look correct. It's sort of a orangey color, if anything. Not that brown is not just dark orange, but it just doesn't look correct. What you're seeing on the video capture is actually more the correct color. Next, I just want to quickly test that this AdLib card here is working, because that's something we actually haven't tested. So, wow, look how slow that is. We will do 3 for AdLib. Yeah, it totally works, and it's coming out of the internal speakers here on the computer. And sure enough, function F1 does mute the audio and turns it back on again. So that's pretty cool. So the one thing that I can confirm now is that the beep speaker is on the motherboard and the OPL audio is separate. It would have been nice if those were combined together into these speakers. That way, for games that use both, you would have that combined sound. My assumption is that the audio output jack on the side of this thing also only outputs the OPL sound and not the beep speaker. A little bit unfortunate. All right, before I do any further testing on this thing, I'm just gonna put it together the rest of the way, give it a little bit of a clean on the outside, put all the little plastic covers back on, and then we can actually run this through a few other tests. All right, I have the Commodore 1084 sitting on the bench. This thing has TTL input, which it's currently set to. The book is all back together, and I have it, of course, connected to the monitor, and this thing is fully reassembled. I did go ahead and remove the stickers from this thing. I'm not a fan. I am not a fan of stickers anywhere on any laptop, including old retro ones like this. So yeah, I peeled those off. All the little plastic doors are back on, front and bottom, or top and bottom. I also put little rubber feet on the bottom of this thing because it didn't have any. So now when it sits on the bench, it's nice and grippy. So will this work with a real 1084 monitor? Let's find out. Here we go. Oh dear. Well, that's interesting. That is interesting indeed. So we have text here, but we are getting basically a green background. And it was working perfectly on the RGB to HDMI as we saw in the video capture. So let me go hook it up to that, see if that is still the case. All right, well, I obviously did something and broke it because the green isn't working at all on the RGB to HDMI. Sorry, it's not focusing on it. It seems that I caused this problem both when I reassembled the case and stuck some hot glue into this and also into the back of the computer. And I obviously dislodged something. Let me quickly try and fix that. And absolutely, when I took the computer apart, which is pretty easy now that I've done it a few times, I noticed the green wire had just come disconnected, and that was because I was sort of pushing the ribbon cable through the hole I had drilled in the case, and it was pushing up against those connections, and it just pushed the green one. I guess I didn't have a very good solder joint. So I just reconnected it, put it back together. Let's see what happens now. Come on. Ah, yes, there we go. It's working awesome. So the fact that I have an LS244 bus driver inside the machine for the CGA output means that A, it should protect if anything bad goes on with that connector that's hanging out the back of the computer. It means it hopefully should protect that logic IC that's sitting on the motherboard that's generating the CGA signals. It's almost like that 244 is a sacrificial chip. Okay, so we're booted up into Landmark speed test. This is version 2. And if I hit function F6, we go from 2.27 to 3.81 megahertz. So that's that turbo speed in effect. Now if we type DIR in here, the scrolling speed is still incredibly slow. And if I push function 6 while it's in the middle of scrolling, I honestly don't even notice any difference whatsoever. So whatever routines are happening in the BIOS that prevent the snow or the flashing during the DIR, make this scrolling speed unbelievably, well, brutally slow, to be honest. Now I'm gonna run the CGA game called Magiduck 1.0, and this is pretty cool in that it uses the special CGA mode where it reprograms the rows and you get a pseudo 16 color graphics mode. Press Y to start the game. Now there may be a ton of snow, but maybe not actually, to be honest. Oh, you know, there won't be any snow because this is running in 40 columns mode and the snow only happens in 80 columns mode. So if we go to new game, we do slot 1. There it is. Check that out. No snow. Really fast animation, even on this slow old computer. So this is like a little platformer. Now it's equivalent of using Petsky text mode essentially to, well, give us this 16 color mode even on old CGA XTs, and it runs really fast, which is frankly pretty awesome. And let's see, I can fire. You're supposed to collect the gems and things like that. And well, yeah, it's really good. Now, doesn't this just look so much better hooked up to a monitor than this garbage? It's really let down by this terrible screen, which is really a shame because I've played with plenty of those like little handheld Nintendo consoles and things that have far better screens than this. Now, albeit they're much smaller than this, but you think a 4x3 screen that would have looked a lot better than this would have been available for this little machine. And considering plenty of work went into designing this. I mean, not just the PCB, but the plastic case and, well, the physical design of it all. It's quite good, actually. I mean, the build quality is not terrible for this little cheap computer. Now, Magiduck was not the only game that existed out there that used that CGA mode, and this is another one. Oh, but it uses 80 columns mode, so we got the snow, and it's Paku Paku, which is an awesome Pac-Man clone for IBM XT and 5150 machines. And unfortunately, well, the snow... Oh, it even has decent sound. Oh, it's using the ad-lib. Okay, well, I didn't even know. Hey, the snow is very minimized, though. All right, well, it has beep speaker sound as well if you don't have an ad-lib. But check out how great this is. I mean, it looks absolutely fantastic to my eyes. And even ignoring that little bit of snow at the top, which is honestly very minimized. Now, the reason why I know it's using ad-lib sound is because the sound is coming out of the speakers around the bezel of the screen. All right, I got them all. Now, when we saw that post about a hardware mod for this thing to restore some kind of cycles or something like that, I think what it's talking about is that this doesn't do the DMA-based DRAM refresh like the original PC. Therefore, this runs a little bit faster and it's not cycle accurate. So with that mod done, I think it makes this thing 100% cycle accurate versus the very first 4.77 megahertz machine. And then it's quite possible that this game is so perfectly tuned for those original machines that the snow is completely minimized and is held outside of the visible refresh area of the screen. And I guess the timing is maybe slightly off on this, which is why most of the time, like right now, there's no snow, and we just get a little bit of a band that runs through the picture. All right, that is going to be it for this video. I played around with this thing enough to know that, well, I think it's a very interesting idea, but there are so many limitations of this particular version of the Book8088. I really can't recommend it. Now, I've heard that there's a version 2 that came out that it has some additional features, like maybe even EGA support built into it. I haven't looked at that, so I can't really speak to it, but this first version, it would have been so nice if they had just included the CGA output on the system, using the buffer and everything. That would have been so simple to add that in, like with just pennies of additional cost. I don't know why it wasn't done, because if it was, it would have been so convenient for using an external screen like this. As far as repairing this machine goes, I really think I had a lucky break with the fact that it worked some of the time, especially when I took it out of storage after a few months, because that enabled me to kind of poke around the motherboard and figure out which chip was bad. I'm not 100% sure that I could have figured that out if it wasn't for that, although I suppose it would have been just a good idea to go ahead and swap at least all the socketed chips, at least the ones that I had spares for, and in the case of this machine, it would have made it work again. If you have one of these machines that didn't work in the same way and you're getting a good 5 volts when you turn it on to those logic ICs, you may as well go ahead and try to procure some of those chips, at least the socketed ones, and swap them out one by one to see if any of them make the computer work. But in the case of the 8288, which was definitely a problem on this board, it probably worked when this thing was fully assembled and tested at the factory or whatever. But then once it got shipped out, the little bond failure that was happening inside that IC just got worse and worse. Now, as I mentioned earlier, that 8288 chip was pulled off another motherboard, like a scrap motherboard that was probably e-wasted a long time ago. And that means that those are removed from boards in who knows what way, like with blowtorches or whatever. And that can damage the bonds inside the chips and can lead to some of these types of failures. With all that said, thanks very much, Ezra, for sending in this computer. I'm really glad to have been able to work on it and modify it to make it better by adding this external CGA. It would be kind of cool to add a toggle switch to the side of this thing that would shut down the internal screen, which would probably make the battery last far longer. I think most of this stuff doesn't take up a lot of power, and the screen is probably the biggest consumer of power inside this machine. And obviously, if you're using it with an external monitor, well, you don't need that internal screen anymore. Anyhow, if you liked this video and found it helpful, a thumbs up would be much appreciated. But if you didn't, you know what to do. Huge thanks to my patrons. Their names are scrolling up the side of the screen. They get early access to videos and occasional live streams and things like that. So you can check out the link in the description below if you want to become a patron. My patrons make it possible that this is my full-time job, and without them, it really wouldn't be possible. So I'm very, very grateful to them, and I really do appreciate the support. Hit subscribe if you haven't already, and check out the second channel and all that other good stuff. And I guess that's going to be that. So stay healthy, stay safe, and I'll see you next time. Bye-bye.